Hi everyone, this is Dr.G.Ravindranath Reddy working as Assistant Professor in MLR Institute of Technology, Hyderabad. So we are discussing a course, Numerical Methods and Integral Transforms. In this course, we have the concept that is interpolation. In that interpolation, in this video we are going to discuss Newton's backward interpolation. So in this we are going to discuss what is backward differences and what is Newton's backward interpolation, when we can use this Newton's backward interpolation, and we'll take some problems on the Newton's backward interpolation concept. Okay, first we will see what is backward differences here. So now, in order to explain these backward differences, I have taken some values of y0, y1, y2, y3 and so on, yn, and its corresponding x values we have taken as x0, x1, x2, x3 and so on, xn. So if you represent these values in the table, so this is the table you will get. So x, y, x0, x1, x2, x3 and so on, and its corresponding y values as y1, y2, so y0, y1, y2, y3 and so on. Okay, so in our hand these are the values of x and its corresponding y values, and the function is unknown function, that is y is equal to f of x. Now take the first two values of y, y0 and y1, and find out the difference, y1 minus y0. So this difference is represented with del y suffix 1. So this del represents the backward difference operator here. So in the Newton's forward differences we have seen y1 minus y0, it is represented with the symbol delta y0, whereas the same difference y1 minus y0 is represented with del y1. Here del represents the backward difference operator. In the forward, this delta represents the forward difference operator. Okay, now we concentrate only on these backward differences, and whereas if you take the next two values y1 and y2, the difference of these two, y2 minus y1, so y2 minus y1 is represented with del y2. Like this we can find out the differences, and we can represent these differences with the standard symbols here. So the differences of these y values we can call it as a first backward differences here. So whatever the values we got in the first backward differences, once again if you find out the differences of these numbers, then we can get our second backward differences here. So already we said that this delta we can call this del, we can call it as a backward difference operator, and which will act as this similar to this delta here. So whatever the values we got in the first forward, if you find out the differences of this first forward differences, we can call it as a second differences here, and these second differences are represented with delta square y suffix minus 2 delta square. So since we are saying that second backward differences, the second backward difference is represented with the delta is del square, not delta, del square. So del square represents the second backward differences of y values here. Okay, so this del square y suffix 2, so we have taken this del y1 and del y2. These are the differences we got for this. In the here the difference of this one is represented with del y1 and this is del y2. So once again if you take the differences of this, these values, so del y2 minus del y1, so this is represented with del square y2, and similarly whatever the differences we got for the next two numbers, that is represented with del square y3. So like this, in each we'll take the differences of whatever the values we got in the present column, and we'll follow this procedure until we get a single value in that particular column here. So whatever we have discussed now, if you reprint this in the tabulated form, then that table we can call it as a backward difference table. Okay, this is our backward difference table. Now we'll see how to represent whatever we have discussed in the previous slide. We'll represent in the table. So we said that these are the values of y. Now you take these values and find out the difference. So this difference is y1 minus y0. So this first time you are finding the differences of these y values here. So we can represent with del and y1. And similarly take these two values here, y2 minus y1. So this is represented with del y2. And take the next two values here. So y3 minus y2. So this is represented with del y3. So del y1, del y2 and del y3. These are the resultant values of first backward differences of y. Now whatever the values we got, once again you find out the differences of these values, then we can get our second backward differences. So if you want to find out the second backward differences of this y, whatever the values we got in the first backward differences, once again you find out the difference of these values, we will get our second backward differences here. So now del y2 minus del y1. So if you find out the differences of this, we will get our second backward differences and is represented with del square y2. And now you take these two values, del y3 second value minus first value, that is del y2. So if you find out the difference of this, we will get some value that is represented with del square y3. Okay, this del square y2 and del square y3, these are the resultant values of second backward differences of y. So now once again you find out the differences of these two numbers, we will get our third backward differences of y. So this is del square y3 minus del square y2. The difference of these two numbers, we can call it as a third backward difference, which is represented with del q y3. So now in this present column we got only one value, so it is not possible to go for the next column because it is not possible to find out the difference of this single value. Okay, so we have to continue this table until we get a single value in that particular column here. So this is the way how we can construct backward difference table here. Now let us take the formula for the, so here now by using this backward interpolation or backward difference table, we have a standard formula, that is we can call it as a Newton's backward interpolation formula. Now we will see how to use this Newton's backward interpolation when we have to apply this Newton's backward interpolation formula. Now we will discuss about this. Now let us suppose that I have taken a data. So this is x values and this is y values. So 0, 1, 2, 3. So these are the x values I have considered and its corresponding y values. You consider some values here, 4, 6, 7. So in general these x values are represented with x0, x1, x2, x3, and its corresponding y values are represented with y0, y1, y2 and y3. Now the function, we don't know the function, so let us consider that function as f of x. Y is equal to f of x. Now my question is, I want to find out the value of y at x is equal to 2.5. This is my problem. For unknown function, this is the data he has given, and now I want to find out the value of this y when x is equal to 2.5. So once if you know the function, then we can substitute that x value in that function, then automatically we can get our y value. But we don't know the function f of x. So now whenever I want to find out this y value at x is equal to 2.5 from the given data, I want to use this data. So first we have to check whether that 2.5 exists or lies in the beginning of the table or ending of the table or in the middle of the table. Now once it is very clear that this 2.5 lies in between 2 and 3. So this 2 and 3, in between this 2 and 3 we get 2.5 will exist. So the 2.5 lies at the ending of the table. So this 2.5 lies at the ending of the table. So whenever the x value lies at the ending of the table, then if you want to find out the value of y at this x value, then we can use this Newton's backward interpolation formula. Once again I will repeat. So whatever the value he has given for x, if that x value lies at the ending of the table, then if you want to find out the value of y, then we can use the concept of Newton's backward interpolation formula. So this is our standard formula to apply this Newton's backward interpolation. So here yn represents the last value of y in the table. So in our problem, suppose in this example, the final value of y is represented with y3. So we can replace that yn with y3 plus p. Now we have to find out the p value here. So the formula to find out the p value is given as x minus xn. Xn is nothing but the last value, terminal value or ending value of the data given in the table. So that 3 is also here, the ending value is 3. So we can replace that xn with 3. And the x is nothing but the where we are going to find out the value of y. So that x value is given as 2.5. And h is nothing but the common difference between the values of x. Now take this 0 and 1, the difference is 1. Take 2, 1 and 2, the difference is 1. Take 2 and 3, the difference is 1. So in between these values of x, we are having a common difference that is equal to 1. That is represented with h value here. So 2 minus 2.5 minus 3 by 1. If you simplify this, you will get our p value here. Okay, we have to substitute that p value. And del yn, del is represents the first backward difference. In that column, we have to consider the last value in that particular column here. And the next term is p into p plus 1. Substitute the values of p and p here. And then you take this del square y suffix n. That is, del square represents the second backward differences of y. Go to the column and consider the last value in that particular column here. So like this, we have to take the Newton's backward interpolation and take the help of this p value and substitute that p value, and del yn, del square yn, del cube yn, del power 4 yn, and we will get all these values from the backward difference table here. Okay, this is about Newton's backward interpolation formula. Now let us take one example how we can use this Newton's backward interpolation formula here. So this is the data. So the following data gives the melting point of an alloy which contains lead and zinc, and find the melting point of alloy containing 74% of lead. Okay, so in the table he has given the percentage of an alloy of lead in that particular alloy and the temperature. So in that alloy, if you want to get this 50% of lead in that alloy, we have to maintain the temperature at 205 degrees. And in order to get the 60% of lead in that particular alloy, we have to maintain 225 degrees temperature. So like this, for each and every temperature, he has given the melting point, that is temperature. For each and percentage of that lead in that alloy, he has given the temperature. Now our question is, in order to get the 74% of lead, how much temperature we have to maintain? That means we have to find out the temperature here. That is our question. So now once if you observe, 74 is the number he has given in the problem. So once if you observe that 74 lies between 70 and 80. So that lies at the ending of the table. So whenever the given value, x value, suppose if you consider that percentage with x, so when x is equal to 74, that 74 lies at the ending of the table, then we have to use Newton's backward interpolation formula to find out the temperature. Like this, we have to analyze the problem and we have to check whether that value lies at the beginning of the table or ending of the table. If it is ending of the table, then by default we can go for the Newton's backward interpolation formula. Okay, so now we'll construct the table here, backward difference table, because we are applying the Newton's backward interpolation formula. So before taking that standard formula, first we have to construct backward difference table for the given data. So this is the data, x values, and this is y values he has given. So in general, these y values can be represented with y0, y1, y2 and y3. Okay, its corresponding x values are x0, x1, x2, x3. Now already we have seen, just now we have seen how to construct this backward difference table. Take the first two values of y, that is y1 and y0, find out the difference here. So 225 minus 205, you will get 20. So this is represented with del y1. Now next you take these two values, find out the difference, which is represented with del y2, and take the next two values, 274 minus 248, you will get 26, that is represented with del y3. So 20, 23 and 26, these are the values we got in the first backward differences of y. Now whatever the values we got in this column, once again you find out the differences and we'll go for the next column, that which contains the backward differences here. So 23 minus 20 will get 20. So this is represented with delta square y suffix minus 2. And next you take this number and next number. So 26 minus 3, 23, you will get 3. So this is represented with del square y3. Okay, 3, with both values we got 3 in the second backward differences. Once again you find out the differences of this, which is 3 minus 3, this is equal to 0, which is represented with del cube y suffix minus 3. So this is last value of x and this is the last value of y. So whenever we use the Newton's backward interpolation, so for that Newton's backward interpolation, whatever the values we got in these lower values early, so we have to consider this value and we have to consider del y3, we have to consider del square y3 and del cube y3. So these are the values we have to consider in the Newton's backward interpolation. So in each column we have to take the last value in that particular column. So now we'll see how to find out that p value. This is our standard formula to find out the p value, x minus xn by h. Xn is nothing but the last value. Our last value in the x column is 80. So you take 80 and we are finding the temperature in order to get 74% of lead in that particular alloy. So you consider that x as 74. 74 minus 80 by 10, you will get this value as minus 0.6. This is our p value here. So now we have completed the backward difference table. Now we got this p value. Now we are ready to take the formula of Newton's backward interpolation. So this is our formula for Newton's backward interpolation, yn p into del yn, del square into yn, del cube into yn. Now we got the value of yn. Yn is nothing but the last value. This is our last value in the table of y column. So we'll substitute that values here. 274, p value we got minus 0.6, del yn, that is we got 26. The next one is del square yn, we got 3. So no need to go for the next column here. In the table we got del cube. So in the table here we got del cube value is equal to 0. 0 into anything equal to 0. So we can neglect this term. Whenever we get this value is equal to 0. Now you consider this and these three terms here and simplify. Then we will get our required y value here. So finally we will get y is equal to 258.04 degrees. So in the alloy, if you want to get that 74 percentage of lead in that particular alloy, we have to maintain the temperature 258.04 degrees. So this is the way how we can apply this Newton's backward interpolation. The main thing is, whenever the x value lies at the ending of the table, given table, then we can go for the Newton's backward interpolation. Then use Newton's backward interpolation formula and substitute the values, whatever the values we got in the backward difference table and p value in that particular formula, then we can get our required y value here. This is the way how we can apply this Newton's backward interpolation formula. Now let us take one more problem, how we can use a single table to apply both Newton's forward and Newton's backward interpolation. So here this is the data here given, and now by using this data we have to find out the value of u suffix 0.5 and we have to find out another value u suffix 3.5. So whenever we consider this one, 0.5 lies at the beginning of the table, that is it lies in between 0 and 1, and whereas this 3.5 lies in between 3 and 4. So 0.5 lies at the beginning of the table and this 3.5 lies at the ending of the table. So in order to find out this, we have to apply Newton's forward interpolation. In order to find out mu suffix 3.5, we have to apply Newton's backward interpolation formula. Okay, so here I will tell you why I have taken this problem here. For both Newton's forward and Newton's backward, no need to construct the forward difference table and backward difference table separately. So once if you construct one difference table, that difference table we can use both for Newton's forward and Newton's backward interpolation. Now we will see how to use that same table for both formulas here. So this is the data. So already we have seen number of problems how to construct the difference table here. So now I am going for the forward difference table here. So as usual, you consider this y naught, this is y naught value. So this is y1, y2, y3 and y4, and find out the differences here. You will get our first difference value, second difference, like this you find out the differences here. So finally you will get that delta power 4y, that is fourth forward differences of y value is equal to 0. So this is the table. So from this table, whenever you are applying Newton's forward interpolation, so whatever the values, beginning values of respective columns, so beginning values in the first y column, you consider that first value as y naught, you take this one, and then the first forward difference column you take the first value, in the second forward difference column you take the first value, in the next column you consider the first value, and the last column you consider that value. So whenever we want to apply this Newton's forward interpolation, we can use the beginning values in that particular columns in the Newton's forward interpolation. Whereas while you are applying the Newton's backward interpolation, you consider the ending values in that particular columns. You use this 54, 35, 18, 6 and 0. Use these values for Newton's backward and use these beginning values, first values for the Newton's forward interpolation formula. So by constructing this single table, by taking these values, we can use the same table for both Newton's forward and Newton's backward interpolation. So now let us take this mu suffix 0.5. So we have seen why we have considered for the Newton's forward interpolation formula. This is the reason. So 0.5 lies at the beginning of the table. So whenever the x value lies at the beginning of the table, by default we can go for the Newton's forward interpolation formula. So this is our Newton's forward interpolation formula. So in our table, so we have stopped our difference table at delta power 4. So we have taken the formula up to delta power 4. Okay. Now take p value. So whenever we want to apply Newton's forward interpolation, we have to take x minus x naught by h. H is the common difference. X is 0.5 and x naught. The initial value of x is 0. Now use these three values and get the value of p. So we get p is equal to 0.5. Now from the table, you take y naught, delta square y naught, delta cube y naught, delta power 4 y naught from the table. That is, y naught is nothing but y column first value. Delta y naught, first forward difference column, first value. Delta square y naught, second forward difference column, take the first value here. Like this, you take all the values here and substitute that values in that standard formula. You will get our required value. Y is equal to 0.125. So this is the value of mu suffix 0.5, that is 0.125. So in order to check whether this value is correct or wrong, once again go to the table, given table. Whatever the value we got, that value should be in between this. Whatever we got, that mu suffix 0.5. So we got that value is equal to 0.125 something. This value must be in between these two values. Okay, like this we can verify whatever the value we got, final answer. Okay, so this is. Now go for the next case, that is finding the value of mu suffix 3.5. So 3.5 lies. In the beginning only we said that 3.5 lies at the ending of the table. So whenever that x value lies at the ending of the table, then we have to go for the Newton's backward interpolation formula. Use the formula, find out the value of p, substitute that p value and these values yn. Yn is nothing but the y column, take the last value of y, del yn. In the next column, you take the last value of y. Like this, in each and every column, you consider the ending value in that particular column and substitute that values here along with the p value. Now simplify this. We got this value is equal to 36.827875. So this value, if you want to check this value, whether this value is right or wrong, once again go to the table and then you take that and check this value must lies between 3 and 4. So its corresponding value is y values. We have to check the values, y values when x is equal to 3 and when x is equal to 4. This value must lie between these two y values here. Okay, so this is one example how we can use, say, single difference table for both Newton's forward and Newton's backward interpolation. So in this video, we have seen the Newton's forward and Newton's backward interpolation formula and how to use this Newton's forward and Newton's backward interpolation formulas in the single table. So in the next video, we'll go for the central differences. So this is about the Newton's forward and Newton's backward. So in the next video, we'll go for the central differences here. So in this video and the previous videos, we have seen whenever the x value lies between beginning of the table, we can choose Newton's forward interpolation. Whenever the x value lies at the ending of the table, we can just now we have seen how to apply this Newton's backward interpolation. Now whenever the x values lies in the middle of the table, not at the beginning, not at the ending, if it lies in the middle of the table, then how we can use this interpolation concept to find out the value of y at x given value of x. So this we will discuss in the next video. Thank you.